we want to find what is the moment around point O. Remember, the moment is a vector quantity. It will have ijk components to it. So we want to make sure that we report our answer with the I, the j, the k components. The diagram is straightforward for this one, but I'll recopy it and I'm going to rotate it a bit. We have this bracket that starts at the origin O and goes up in the z direction by 10 meters. And that comes out 3 meters. And at this point I'm calling A, I have a force given to us in components already as negative 2I plus 5J plus K. And that force is in newtons. Like when we were working with particle equilibrium, it's going to be helpful to be labeling our points that are going to be helpful to us, like point A where we're applying this force. We want to put its coordinates, and it's going to help us find the position vector in subsequent steps. Or if we need unit vectors, it's going to help with that as well. All right, so the coordinates of A, if we have to go up by 10 in the z, we have to go over by 3 in the positive y, and we don't have to travel at all in the x. So it's going to be 0, positive 3 in the y, 10 in the z, and this will be in meters. So in the equations, if we want to find the moment around point O, we have to find all of the, for right now, just all the forces that cause a moment around point O. So any force that does not have its line of action pass through O is going to potentially be creating a moment around it. So we have this force F here that does not pass directly through O. So that means that we are going to find what is the moment caused by it using this cross product. So it's R cross F. We need to determine what is the R that we're using so that we're doing this properly. Right, so again, the rule is that the position vector we use starts at the point where we want to know the moment. In this example, it's O. And it ends where the force, for this force, where it is acting. Here, we're saying it's acting at point A. So I need to use position vector ROA here. This is acting at A, it just doesn't have a subscript like it did in the slides. Right, so starts at O, because that's where we want to find the moment about. It ends at A, because that's where this force is being applied. If we have multiple forces, each one might be associated with a different position vector that will all start at O, but they will all end wherever their force they're paired with is acting. So graphically, we could draw this vector in, goes from O, and points towards A. So we're crossing this force with this position, or really the opposite, this position with this force. F we already know in component form because it was provided to us. So ROA, I just need to write its components. And because I put the coordinates of A, and I know the coordinates of O are 0, 0, 0, it's just going to be end point minus start point. So that will be 3J plus 10K. Again, have this in components, have this in components. We know from the second section that we can write a cross product as a 3 by 3 determinant. First row is always ijk. The second row is the components, the coefficients of the components of ROA, or really the R vector generally. So in this case, it's 0 in the I, 3 in the j, 10 in the k. And this is measured in meters. One thing to note that occasionally comes up, it's the position vector cross the force vector. For this step, I am not using a unit vector. I'm using the actual values of the position. So it's not normalized for this. Third row, the components of my second vector in the cross product, F, which was given to me. So -2, 5, and 1. and this is in newtons. We know from section 2 how we can expand a 3 by 3 determinant into 3 2 by 2 determinants by using cofactors, or there are other methods for 3 by 3. I'm always going to be using cofactors though. So remember what we do is we put a 2 by 2 determinant in front of I that's made up of all the values not in the I row and not in the I column. So that what's left is 310, 5, 1. We then subtract the same method in front of J. So not the column, not the row, leaves 0, 10, negative 2, and 1. And then we add the same thing in front of K, 0, 3, negative 2, and 5. Again, when we have a 2 by 2 determinant, this is equal to the product of the main diagonal, the 3 and the 1 in this case, minus the product of the off diagonal, the 10 and the 5. So this would be positive 3 minus 50, minus 0 times 1 is 0, minus negative 20 is the same as plus 20. And we have 0 minus negative 6 is plus 6, k. Okay, so simplifying this a little bit further, we get negative 47i minus positive 20j plus positive 6k. And this is, I'll rewrite it over here, this is my moment around point O. The moment will have units of force times distance. So luckily, I kept track of that over here, so it will be in units of Newton meters.